Okay, here we are. It's the physics video lecture. Physics 203, video lecture 25. Okay, we're working on fluid mechanics. I'm going to just get us up to speed where we've been, and then I'll tell you what we're trying to accomplish now. Because the subject is huge. I've got the notes for a full semester class here, and we have a couple of hours. So let's review what we've done briefly, and then we'll kind of outline what we're trying to accomplish here. Okay, so good. Fluid mechanics. We have a velocity field, X, Y, Z, and T, that we're trying to discover, determine, learn its properties for a fluid flow. And our equations are continuity. So I'll just write here velocity field vector. And then we have the continuity equation, d rho dt plus divergence of rho times b is equal to 0. And then we said, well, if the density is constant and the divergence of the velocity is 0, which we needed for our Hamilton mechanics discussion, so that already served us. It will again. So this is continuity, and that was conservation of mass. Continuity equation. The other thing we had was Euler's equation. V dot gradient applied to V minus 1 over rho gradient of the pressure. Okay. And that came straight out of Newton's law. So even though it's Euler's equation, it's the expression of Newton's law. Okay. And what we found out of these things here so far, actually that rotating bucket example that we ended with is kind of interesting, because you guessed the solution. It's really just a rigid solid that's rotating, but it actually solves this equation, and then you're able to, from the pressure distribution, determine the curvature of the surface, right, of the surfacer, which was paraboloid. So that's a nice expression, nice example. But then we showed that there are flows with curl of V not equal to 0, and there are flows with curl of V is equal to 0. And we have to investigate this a little bit more. Okay, so the curl V not equal to 0 was, of course, that rotating bucket. Curl V equals 0 was an interesting version of that same rotational thing when it decays with a certain power. Okay, I put that as a homework assignment, but I think I stated the answer as well. It's an interesting problem, by the way. Good. So what are we trying to accomplish? Because there's just a wealth of things. It's a pretty technical subject. What we want to do is spend a little more time about these curl-free fields, and then we want to get wave equations. So we want to talk about the curl-free flow, and then use these equations to get a wave equation. That's where we're headed, and that's what we need to investigate a bit until we can segue back into mechanics in into Hamiltonian mechanics in a very surprising way. Okay, so what we need to do is a little bit more with these curl-free fields. Okay, so let's just put this here. Our goal wave equation. So waves in fluids, you can think sound waves in air, sound waves in water. Yeah, I have notes for the surface waves, water waves, which are also immensely interesting, but we don't have time for everything. Okay, so we're trying to get to the wave equation, sound waves. Okay, but first, let's talk a bit about a reformulation of some of these things here. I'm gonna work off my notes here. Okay, we're gonna reformulate Euler's equation, and we'll begin with just writing it v dot grad v. Let's get a pen that writes here. Okay, let's try this. Yeah, I can, there we go. Minus 1 over rho gradient of P plus G, right? We said if we're in an external field, we add the external field, and of course it's often gravity. Now, let me just do some alternate expressions right here. We can have gradient at the minus sign here, minus. We can have minus gradient P over rho minus G dot R, okay? This will just give us our uniform grad, as you can see if you try this out, it'll just give us our uniform gravitational field pointing in the down direction, okay? Or, extending this, or minus gradient of W, and here I'm just going to write, without proof, the appropriate thermodynamic potential. In other words, it's possible to bring everything inside the gradient, and this here I kind of owed you from last time. You can incorporate this into the definition of the pressure, okay? And in fact, you can even incorporate this, like I said, you can incorporate it this way, which covers that. You can incorporate it into the definition of the pressure if need be. Okay. So I'm just going to write the appropriate thermodynamic potential which we could do if we had more time, comma, the enthalpy. But we're not going to have to worry about that, just to be systematic and complete about it. Okay, so there's Euler's equation. Now we're going to reformulate this using a grad. There. Using an identity from vector algebra. Vector calculus. So use this identity. If it were serious, we'd do this for a homework assignment, but we just took it right out of Jackson. Okay, so gradient of the vector of the scalar product of two vectors equals A dot grad B plus B dot grad A, which we recognize, of course, as that type of operator right there, plus A cross curl B plus B cross curl A. Well, you don't want to prove this today, but it's not impossible, just a lot of derivatives. What that allows us to do is rewrite Euler's equation. Namely, if A and B are both the velocity, then you're looking at the gradient v squared equals this plus this, or the gradient v squared over 2 can replace this thing right here. Now then you have these curl terms, but we're talking about, we're going to be interested in flows where the curl equals 0. So the curl of v is going to be in these guys here. So to complete this thought and take A equals B equals the velocity vector that we're talking about here. And okay, I'll erase this. Well, we're going to write it down with the curl first. So there's a useful vector identity. Let's go ahead and erase this. So we're working with Euler's equation, and we get this. d v dt plus gradient v squared over 2 minus v cross curl of v equals minus gradient. And I'm going to put P over rho inside. If rho is incompressible, if rho is constant, this is legit. If rho is not constant, we can imagine we've got the appropriate thermodynamic potential. Okay, it's not going to cause us any grief. Good. So if the curl of V is 0, we have a simplification here. Because then we would have dv dt, plus these remaining things. But in particular, so let's consider flows where curl of V is equal to 0. Then, in addition to this term vanishing here, we can express V as the gradient of what's called the velocity potential. Right? Because that's a property of a curl-free field, right? It can be expressed as the gradient of a potential. So not V, but phi here is the velocity potential. And it's going to simplify things a lot. I'm going to add a note. Also, if we have an incompressible fluid, if the fluid is incompressible, if the fluid's incompressible, we're going to end up with another differential equation. So let's just write this down. The fluid is also incompressible, then divergence of V is equal to 0. And that means we're looking at divergence of the gradient where del squared phi is equal to 0. That's not bad, right? Because then you have potential equation, and you're talking about what are called potential flows. Potential flows. Okay. So yeah, I'm going to put a red box around this. This is the important point here. We've got this velocity potential for the case of the curl being equal to 0. Now let's write this when we have all these gradient terms. So now we have the gradient out of this equation here of d phi dt. See what I did? V is the gradient of phi, and I just switched the order of the differentiation, plus V squared over 2 plus P over rho is equal to 0. Okay. Switch to it. I'm using this thing with the curl being equal to 0. And so we can write d phi dt plus V squared over 2 plus P over rho is some unknown function of time. But we don't even have to be concerned about this function of time, because we can absorb its definition into the definition of phi. So because of that, we have d phi dt plus V squared over 2 P over rho can be thought of as just some constant or even 0. Okay? It's going to link all of these things. Good. So let's keep going here. Now, taking this equation up here, for an example, let's consider a steady flow that is time independent. Consider a steady flow. Think streamlines, that, steady flow dv dt partial is equal to 0 in a steady flow. Okay. That's something where if you were to drop some dye in a fluid flow, you just see some streamlines. Say there's an object that it's going around. Okay, you get just some steady flow. Okay. So in that case, d phi dt is constant, or 0, it's actually 0. And in that case, we can have V squared over 2 plus P over rho is constant. And as I argued about incorporating the pressure, no longer in here, previous board, incorporating the gravitational field into the pressure, we can also have, and I'll put a note there because this isn't like a direct implication of this, but if we incorporate the pressure into here, then what do we have? Plus P over rho plus G times Z equals constant. So yeah, a note here, see about the previous incorporation of the pressure of gravity. Incorporate G in the pressure expression, which is in your notes. Okay, but I wanted to get to this expression here because this is Bernoulli's equation. So that gives you some idea how we go from systematically and obtain Bernoulli's equation fairly systematically. Okay, so Bernoulli's equation, and this equation has really nice applications. So let me just rewrite it over here where I have a little room. This is something you should look up in your undergrad lower division textbook in the fluid mechanics chapter. There's always a nice little section on Bernoulli's equation and its applications. You'll typically see it in this form here. P plus 1/2 rho V squared plus rho GZ is equal to a constant along a streamline. And I have a bunch of applications here, but I don't know if I'm going to go there. let's see. Well, I have to say a couple things about Bernoulli's equation. Example. A great example is the flow through a constriction. And let's say the flow, you can think of a pipe with a constriction. And this is 1, this is 2, this is back to 1 again. And you're going to say, okay, the z is constant. It's pretty poorly drawn, but okay. The z is constant here, okay? We're talking about flow, which I'll make red. We've got a streamlined flow through a constriction. What happened over here? So I can label 1.1 and 1.2, and then I can say piece of 1 plus 1/2 rho v1 squared equals piece of 2 plus 1/2 rho v2 squared. Okay. Well, the continuity equation guarantees us that the speed is higher, okay, it's faster here at 2 than it is at 1. So what that means is, since we have a constant across this expression here, that the pressure must be lower when the speed is higher. Okay? That's not intuitive, and it shows itself in many examples and situations. So because of this scenario, yeah, let's write that down in words just to make sure we have it. So therefore, higher speed, lower pressure. Okay. So that's all we're going to do with Bernoulli's equation. But look things up on Bernoulli's equation. Very, very interesting examples. Also amazing that we're getting this as a solution to the Euler equations, which are, of course, incredibly involved. But one more caveat: these ideal flow, these potential flows are for ideal fluids, and the equations actually break down. Takes a lot of judgment to apply these things. Anyway, a really, really rich subject. So you got Bernoulli's equation. If you never saw it, you saw it now, but this is early material that you probably haven't seen in a long time. Good, so let's see, we have that. Yeah, a couple of other things here. Let me set this up. Yeah, actually this point right here, this kind of implies that there's another way to get potential flows, and we've got a v squared, so if the velocities are very small, we might expect to get a potential flow. Okay. In the limit of v goes to 0, sure, we have the potential, okay, but that's a trivial one. But when v is very small, you might expect to get a potential flow, and that's what we're going to look at next. Very small velocities, and in particular, small velocities due to the fact that we're talking oscillations. So small oscillations in a fluid are our next task, and let's see here. I can leave some of this stuff up. Yeah, actually we're going to work off of this again. So I'm going to erase everything here. Right, so we're still looking at flows when the velocity is small. Now we got to turn the argument around. So okay, I'm going to erase the whole thing. We can go back to the Euler equation. So next, consider small oscillations. We have small oscillations in a fluid, maybe due to the fact that there's an oscillating body in the fluid. But we're going to go back to Euler's equation, dv dt, p dot grad v equals minus gradient. I'm going to go ahead and put p over rho in here, even though we're not strictly claiming that it's incompressible, because we can always put the appropriate thermodynamic potential in there. Okay, so that's no problem. But anyway, this here, if we have small oscillations, this is a nonlinear term. It's nonlinear in V, and therefore this is very small. And we're just going to neglect it. So if we have small oscillations, we neglect the V squared because it's very small. Then we have dV dt equals minus gradient p over rho. And then we're going to take the curl of both sides. Okay. So let's see which way I put that. Yes. So the curl of dV dt going to equal to minus the curl of the gradient, which of course, not curl of gradient. Okay. The curl of the gradient is identically 0. Okay. So what that tells us is that the time derivative of the curl of V, and I'm just exchanging derivatives, is equal to 0. So we have the curl of V is constant. Okay. So the curl of V is constant under these assumptions here, namely small oscillations where these terms can be neglected. But if the curl of V is constant, what's the value of that constant? Well, because these are small oscillations, we know that the time average is going to be equal to 0. Okay. The time average of small oscillations equals 0. Therefore, our constant equals 0. So our constant equals 0, and the curl of the velocity really is equal to 0. Right, to the approximation where you can neglect these quadratic terms. And if the curl is 0, I'll complete my thought up here. If the curl is 0, then we have a potential flow. So constant equals 0. Therefore, small oscillations, which is to say, small oscillations in a fluid or flows due to a small oscillation are a potential flow. And what's so good about a potential flow? Namely, they have a velocity potential. So we're not worried about the potential equation right now, we're just worried about having a V being equal to the gradient of phi x, y, z, and t. And that time-dependent equation that I erased is also going to hold true. So good, I'll put those results all together and then we'll see where we stand. Okay, that's excellent. Good, let's check the time. Okay. So that's what we needed in order to talk about sound, and in particular the wave equation, and then talk about sound. So, like I said, there's an enormous number of things that we can do in terms of fluid flows, potential theory, Bernoulli's equation, the continuity equation. But we want to get the wave equation and save the other stuff for a longer course in fluid mechanics. But this is, as far as what we've done though, it's pretty legit and thorough. So as far as your notes are concerned, you could try to make sure you get every missing step understood. Have plenty of space in between, and you'll be getting your money's worth. Good, so next is ideal fluids sound, we're going to call it. So I'll just set everything up that we have and that we need. Ideal fluids sound, and by that I mean we're going to get to the wave equation. So we have d rho dt divergence rho v equals 0, right? We have our continuity equation. We have Euler's equation. Gradient pressure. And we had S equals constant. So the entropy is constant. This is a system with no dissipation. And we now know that if curl of V equals 0, then V is the gradient of a velocity, of potential, velocity potential. And I may put this pressure relation in here as well. Yeah, I'll even put this here. Is minus rho d phi dt, comma, when v squared is small. Put that here in parentheses because we're going to make use of it. We could have actually also put the entire relation there that we had up on the board a minute ago. Okay, so what we're going to do is small amplitude oscillations, which is basically going to turn into a linearization of these two equations. Okay. Right now they're fully there. The linearization is going to end up dropping this quadratic term here, but we'll still have stuff to do with it. So put your next small amplitude oscillations. Now, one thing to notice is we can't claim constant density. Okay, we're going to need density to not be constant. So small amplitude oscillations in a compressible fluid. Okay, because they're small amplitude, of course we get rid of the v squared terms. So first, v dot grad v is negligible. And v is equal to the gradient of phi, which we'll end up using. So the linearization is going to proceed as follows. What we're going to do is let rho equal rho 0 plus rho prime, p equal p0 plus p prime. So rho 0 and p0 are constants, and rho prime and p prime are the fluctuations around that constant value. Rho 0, p0 are constant. Rho prime divided by rho 0 much less than 1, right? It's a small fluctuation. V is also small. Okay, so V is small, this is negligible, that's the idea. Good, so let's go ahead and see what happens. Okay, we're just going to keep these up here for the rest of the time until we get our result. That's what we're working with. So we're plugging these expressions into these simplified equations up here. So we have d dt rho 0 plus rho prime plus the divergence of rho 0 plus rho prime times v equals 0. Because v is small itself, it doesn't need anything smaller, so. Equals minus 1 over rho 0 plus rho prime times the gradient of p0 plus p prime. Okay. So how do these things simplify? That, of course, is going to differentiate to 0, so we have d rho prime dt, and then we have a couple of terms here. So the divergence, so we'll have rho 0 divergence of v plus rho 1 rho versus divergence plus divergence of rho 1v plus divergence of rho 1v. But this is small to second order, okay? Because v itself is small, rho 1 is small. So this we can get rid of. So how about the second equation here? Here we have dv dt. Now this will be approximately, we can neglect the rho prime with respect to the rho in the denominator there, so we can just keep a minus 1 over rho 0. And we will have a gradient P0 vanishes, gradient P prime vanishes. P prime. If you wanted to do a fancier expansion, you could do 1 over rho 0 plus rho prime equals 1 over rho 0 prime over rho 0. And then you would expand this. One minus rho prime over rho 0. That'd be your first approximation. But again, that would have given you a small quantity being multiplied with whatever follows, which would be much smaller than this one. Okay. So this is good as well. So good. We have these two. And what about the S being equal to constant, the entropy being constant in the fluid? I'm going to do a little expansion there. Yeah, good. So with the entropy, we can do the following. We're going to understand P as being a function of rho, and then we would have P0 plus dP d rho times rho prime. In fact, I can write it like that, plus and so on. So that's just the linear expansion when you have pressure as a function of density. And you could also do density as a function of pressure, okay? But what we're going to make use of S being constant in that this derivative has to be taken at S equals constant. So S 0, I can put it there. I have it on my notes. Yeah, we'll just put an S there, indicating that S is constant. In other words, this partial derivative at constant S. Okay, so we have the ingredients now. I'm going to put these two together. Am I numbering them? In fact, let's draw the conclusion from this one right here. So if we can expand P like this, and since this is P0, this is P prime. So what we have is a small fluctuation in P there. P prime is equal to dP d rho evaluated at rho 0, I'll put it that way, constant S. Okay, so that's our P prime. So that's our third equation. I guess I'll number these. I guess I will erase what's up there. Okay, so it's 1, 2, and 3. So what we're going to do now is differentiate the continuity equation with respect to time. Remember, this one's already gone, this is equation 1. So next, differentiate equation 1 with respect to time. So what do we have here? We have d squared rho prime dt squared plus rho 0 divergence of dv dt. So we're really generous about exchanging the order of differentiations. Okay, divergence of dv dt right there equals 0. We can do as a next step, we've got this here, plus rho 0, divergence of, but our dv dt is equal to minus 1 over rho 0 gradient p prime. So minus 1 over rho 0 gradient. But what is our p prime? Our p prime is dp d rho 0 at constant s. Actually, I'm missing something there. Rho times rho prime. Okay. Prime. Complete that red square. Alrighty. Right, that was taken from here. Right from here. Okay, so what happens? We'll put all these things in. So gradient p prime, and the p prime we'll put in here d p d rho 0 constant s. We'll write it that way. Rho prime. Good. So now we have a bunch of constants. Rho 0 is a constant here, rho 0 is a constant there. This derivative taken at constant s is also a constant. So this cancels and this derivative comes out. Fantastic. Okay, here we go. So what we have is finally d squared rho prime dt squared equals, get rid of the minus sign, these two guys cancel, this one comes out, equals dp d rho 0 constant s. Yeah, eventually we'll drop all those subscripts, no, not about div grad rho prime, del squared rho prime. Okay. And this is manifestly the wave equation, okay, for the density. And since we already have v being used often enough, we're going to call this wave speed c. C squared is this dp d rho constant s. That's the wave speed squared. Okay, so that's fantastic. We've got the wave equation for the density. There's the wave speed. And because of this idea here, it's clear that if you have a wave speed for the density, you also have one for the pressure, right? You could just as well write pressure as a function of density. Okay. So we have the wave equation for the density fluctuation, and we have the wave equation for the pressure fluctuation. We need to get the wave equation for the velocity as well, and then we'll be complete. Okay. Now there are a couple of ways to do that. Yeah, let's do this. Let's do this right here. So I want to differentiate, I don't want to erase everything here. Let's see. My numbered equations. Actually, good. I'm going to keep my numbered equations up there. So I'll send these back up and erase the rest of this. But yeah, we have the wave equation. We could have done the same thing with P prime instead of rho prime. Okay. So we have both of those. Good, I'll erase these here. Next, we're going to differentiate equation 2 with respect to time, because of course we'll have the d squared v dt squared. See what happens. So d dt equation 2. So what do we get? We get dv dt squared equals minus 1 over rho naught gradient dp prime dt. Okay. But dp prime dt is up here. In fact, I'm going to, since we see what we've got there, I'm going to plug that in right away. So gradient p prime dp prime dt, because we've differentiated with one. Let's just do that. Okay. So the next thing we're going to do is plug in dp prime dt. So equals minus 1 over rho naught gradient, and we have negative rho naught divergence of v equals grad div of v. So here we have to pull out something we probably don't have memorized. Oh, I'm missing something here. My bad. There's the problem. This is not dp prime dt, the rho prime dt. So, it's back up here. Here we go, once more with feeling. 1 over rho naught gradient, I have to do the transformation to rho, so that's dp d rho prime dt. Okay. So I have 1 over rho naught dp d rho, which is of course constant. And then I've got the gradient of d rho prime dt, and now I can plug that in there, minus rho naught divergence v. Okay, so here's where that, pardon me, here's where that identity is going to come into play. The row knots are going to cancel. We got the minus times minus is plus. So we end up with d p d rho grad div v, like that. Okay, dp, d rho, constant s, grad div. So who remembers what grad div is? It is del squared v plus v cross curl of v. Go ahead and look this one up in the Jackson, is usually where I find these things. Okay. But what do you know? Curl of v is supposed to vanish. Okay. Potential flow, small oscillation. So that's why we can kill this one. And we again have our wave equation. So just to show you what we have, we've got d squared v dt squared, and we're left with this. So we have now constant s del squared v and the same thing, d squared rho prime dt squared and del squared p prime dt squared. So we've got wave equations for the whole thing. Del squared p prime, and I've got my definition of c squared constant s. So there you have it. This is what we've arrived at. We're not quite done yet. Let's see what we have going on time-wise. Yeah, we'll go over the hour a bit. Okay, so under these assumptions, curl-free, linearization of continuity and Euler equation, we get wave equations for the velocity field, and there's the speed squared. We get wave equation for the density fluctuation. We get a wave equation for the pressure fluctuation. Okay, so I have a bit more on this subject. I got quite a bit more. Okay, let's see what we're going to do here. We'll put that in words, what I just said. We'll write it down just to make sure everybody has it. Wave equations for v rho prime p prime. Remember, that's the pressure fluctuation. Okay, what I want to do last is express all of these things in terms of the potential. This is a real simplifying step because we've got a wave equation for a vector and two scalars, but there's one wave equation that will govern them all. So all quantities, so you really want to do this, and we're going to, can be expressed in terms of the velocity potential. Phi. So we have V is equal to the gradient of phi And it's basically trivial. If you have the wave equation being satisfied here, you're going to have it satisfied here. Just differentiate, pull the gradient in front of everything. So let me just write these down. And we also have P prime is equal to minus rho naught d phi dt. Again, if phi, P prime satisfies a wave equation, then so does d phi dt, then so does phi, okay? So that's going to satisfy the wave equation, and if P prime, then rho prime, which is just proportional to T prime, was 1 over d rho not constant s times P prime. Okay. So all of these satisfy the wave equation, and therefore, if you solve the wave equation for phi under the appropriate conditions, then you can, you can get v, you can get p prime, you can get rho prime. Okay. So, one more important result. Let me see if I need to. So I'm going to erase this. Phi satisfies the wave equation, d squared phi t squared. Phi equals phi of x, y, z, t, and c squared, as we have before, dp prime, actual, just dp d rho, constant s. Okay, so that makes for really compact work. Now the last result I want to get is for a traveling plane wave. So this will actually be a physical result. We've obtained the wave equation, and we'll get a physical property of waves in a fluid out of this. So now consider a plane wave moving to the right. So my idea here is that we've got x, y, z this time, plane wave moving to the right. Here's my wave. Except I'm really just looking at a pulse. So phi of x, y, z, and t is simply going to be equal to phi of x and t. And if it's just a pulse, it's phi of x minus ct. I assume people have seen this, right? Phi of x minus ct. for some function phi of x of one variable that would form this pulse. For example, this red pulse here is phi of x. And as t runs, the x minus ct equals 0 point moves to the right. Okay, so that's a right traveling plane wave. And now let's see what we can get. What we really want. So now, gradient of phi is equal to phi prime. Let me write it this way. So it's a vector, right? d phi dx, d phi dy, d phi dz. It's a vector with those three components. One of them, phi prime of x minus ct. The other two components, 0. So the only velocity component is the x component of the velocity. And what that means is that a traveling plane wave in a fluid is a longitudinal wave. When you're doing electricity and magnetism, you're always talking about transverse waves. Here we're talking about a longitudinal wave. So, waves in a fluid or longitudinal waves as opposed to transverse. I'll just write not transverse waves. Okay, so that's an important physical point that you've probably heard made. You've heard it made before, but you probably have not seen the proof of it. And the proof's pretty involved since we had to do quite a bit of work to get here. But very good. So I think that's where we're going to leave it. What we're going to do next is just discuss some properties of waves, of functions that solve a wave equation. So our next task is going to be to discuss this thing in wave equations, and it'll be certainly review, but there's nothing wrong with that. And good. Okay, so that was pretty good session today. See you guys next time.